Hello, welcome to CoNGA 22, the Conference on Next Generation Arithmetic. This is, I think, the third time we have done this conference, and it's the first time we've done it with this mixed virtual and physical deal that we have to do for conferences these days. So I am now relocated to the United States after 6 years in Singapore, where they sponsored me to develop a more hardware-friendly form of arithmetic, which bore fruit almost exactly 5 years ago. It was 5 years and 1 month ago that the talk at Stanford University showed people how to do something that was an effective replacement for floating point arithmetic that was based on mathematical principles and not just defining fields the way people had done for so long and the way the IEEE standard had done. That started a revolution that I was really not ready for or would not have believed possible, because generally when you introduce a new idea, you get a lot of resistance. Parallel processing was like that. It took forever for people to adapt to the idea of parallel processing. And there are still people who resist it and would much rather program in serial. But the introduction of Posit arithmetic caught fire. And if you go onto Wikipedia and look up arithmetic, you'll find a table of all of the projects going on worldwide involving next generation arithmetic and posits in particular. And I think it's around 30. Those are the ones that have announced and are willing to be public about it. There, I know quite a few that are doing things in secret, especially the neural network companies are building things without telling anybody because they see the competitive advantage. I know that posits are being used in 5G networks currently. It gives an advantage to the signal to noise ratio there that is not always revealed to the public, but they're there. So CoNGA isn't just about posits. It never has been. It's always been the conference that's willing to look forward and to think about new ways to represent real numbers with computers, because this has been such a treacherous field for so long, and people have become numb to the problems of using floating point arithmetic. They recognize that there's always rounding errors, that they don't obey the laws of mathematics, they don't have associativity and things like that. But it really takes years to learn all of the pitfalls and all the dangers. And there are a lot of those dangers that can actually be eliminated and made to be much, much more friendly. And we're willing to look at anything that will help that problem. So you won't just see papers on Posit arithmetic at CoNGA. And I hope we always do have a more broad vision of what to do, because these things are still being tuned and formed, and there's still a lot of good ideas to come, I'm sure. The acceptance rate for CoNGA was 67%. We were embarrassed by the number of really good papers that came in. If we hadn't had good papers, we would simply have shortened the conference, but we are going to fill 2 days with a lot of really interesting stuff, some breakthrough things. We are approaching very fast the ratification of the Posit standard, and it's been through about 5 years, and you really do want to take a lot of time making a standard, because you can make a lot of mistakes and then they're set in stone and you can't change them. But we don't want to make that mistake. We want to make sure that we can learn from our mistakes before we codify it. And so I think what we've got is going to be as popular and as influential as the IEEE 754 standard once it gets out. We will have a session to discuss that standard at the very end of CoNGA, and that'll be the kind of open-ended ending for the day 3 of SC Asia, on March 3rd. And by the way, one of the things that made the standard possible was the solution to the problem that you're going to hear discussed by Professor Santosh Nagarakatte here as our keynote speaker. I want to say something about where CoNGA really came from. Besides the enthusiasm we saw for the new arithmetic, we tried to submit some papers to the Arith conference, which traditionally has been the place where you put papers on computer arithmetic. But we discovered that it was a shrinking conference and that it was only interested in papers that reinforce the existing floating point standard, not that try to challenge it and say there could be something better. We submitted, I say we, I mean the Posit community, submitted, I think, 8 papers to Arith last year to see if we could get them to accept this new idea and start actually allowing us to talk about it at Arith. All 8 of them were rejected, including some things that were really quite revolutionary and solved long-standing problems in mathematics. I was amused by this more than I was offended. I said, okay, we need to bring back CoNGA. We had done 2 CoNGA conferences. If we can't get these papers out through Arith, we have to have our own conference. I'm glad that Springer is going to be publishing the proceedings of this. So all of these excellent papers are going to be available to the community. There's an interesting opposition coming out of the University of Lyon. Perhaps I shouldn't name names, but if you look at the authors of a paper called Posits, the Good, the Bad, and the Ugly, you will see with your own eyes the kind of direct opposition to any kind of new ideas, where they will do things like translate posit format into floating point format, apply floating point hardware, translate it back to posits, and then conclude that posits are more expensive than floats. So finally, we're starting to see a different approach to to posit hardware, and we will get some papers about that that will I think reveal that that maybe it's time to change, that posits actually may be better than floats in almost every respect. Now, one of the things that the old timers hang on to dearly in the computer arithmetic is something called the table maker's dilemma. And this is the idea that when you compute transcendental functions, you cannot predict ahead of time how much work it will take to be able to round it correctly. They can be extremely close to just dead on between two representable numbers, and you don't know whether it's going to round up or round down. Sometimes you get 0.49 and followed by 25 nines trying to calculate this, and the only thing you can do is stop, recalculate it with 200-bit precision, use a huge polynomial, and so on. And that problem is 400 years old. It was William Kahn who coined the term table maker's dilemma. Because it's so hard to round, the Intel math kernel library, the GCC library, they get a pretty good, accurate representation, but they don't get it exactly right. There are always cases that do not round correctly. This is the source of irreproducibility in real number arithmetic worldwide. This is the biggest one, because if you can't depend upon math libraries to give you the exact same answer every time to the last bit, then you can say it is futile. No one can make a computing environment that gives you bitwise reproducibility in real number arithmetic. Well, as I said, hold my beer, because I think there is a way to do this. And it was an insight that they were approaching the problem quite wrong. And that is what I'm delighted to see, that Santosh Nagarakatte took this idea and he really ran with it. He greatly improved on the original insight, put his team of brilliant graduate students on it, and came up with a solution that he's made available to the world. I'm told that his GitHub is quite easy to use. People have tapped into it. And because we now know it is practical to have perfectly rounded math libraries, that whole curtain of it's just intractable, don't even try to do it, has come down. And the POSIT standard requires that all transcendental function, all math functions, be rounded correctly. There are no exceptions, which means you can get identical results from one system to another for the first time. That's quite a breakthrough. So this, when some mathematician solves a problem that's been around for 400 years, it's a pretty big deal. And I thought that a keynote talk on that was very appropriate. So let's see if there's anything else I want to mention before we go into Santosh's talk. Let's see. I should mention that I am no longer with the National University of Singapore. I ended my contract with them on November 30th, and I am now relocated in Arizona. So I'm coming to you from 9 time zones away. Well, actually plus 15, I guess, formally. And I will be staying up until 3 a.m. as your host for this conference, and trying to, if the camera comes back on and you get it, something like that, I'd probably fall asleep. I hope someone says something to me loudly so I can get back up. But this is the first time we've tried something this complicated and this difficult of managing a hybrid physical and virtual conference. We have outstanding help from the MICE studio that is managing this. I've been impressed with just the huge amount of work that has gone in on the Singapore side. But all of this has had to be coordinated with a very large time difference. And I'm very thankful to the SC Asia people for once again allowing us to be a conference within a conference. We inherit all of the support people that they have set up for us. and don't have to, do it from scratch like we did the first 2 years. So I think this is going to probably be an ongoing thing, that we will always be a sub-track within SC Asia, but a big one, almost a conference in itself, but managed with the help of those people. So I would like to introduce Professor Santosh Nagarakatte. He is an associate professor and undergraduate program director of computer science at Rutgers. He obtained his PhD from the University of Pennsylvania and in 2012. His research interests are in hardware-software interfaces and spanning programming languages, compilers, software engineering, and computer architecture. His papers have been selected as IEEE Micro Top Picks Papers of Computer Architecture Conferences in 2010 and 2013. He received the NSF Career Award in 2015, ACM SIGPlan PLDI 2015 Distinguished Paper Award, and ACM SIGSOFT ICSE 2016 Distinguished Paper Award for his research on LLVM compiler verification. His papers have been selected as the 2016 SIGPlan Research Highlights Paper and 2018 Communication of the ACM Research Highlights Paper. His papers on correctly rounded elementary functions have been recognized with the ACM SIGPlan PLDI 2021 Distinguished Paper Award and the ACM SIGPlan POPL 2022 Distinguished Paper Award. Not bad for a guy who's only been a professor for less than 10 years. Really impressive. Santosh, would you like to start just slightly early? I think we're ready to go.
Okay, so can you guys hear me? Okay, so awesome. Thanks, John, for the generous introduction. And I thank the organizers for inviting me to give this talk. So today I'm going to talk about our project, which I call RLIBM, to generate correctly rounded libraries. So my goal of from this talk is to show you some evidence that it's feasible to design both fast and correct math libraries. Okay, so you don't wake up and start designing math libraries, right? How did I? Let me tell you a story about how I started designing math libraries. Okay, so for a long time, I have been working on proving the correctness of compiler optimizations. And we have had some luck where like our tools for compiler optimizations have been adopted by industry. So effectively, we take compiler optimizations, encode it into first order logic, and use automated theorem provers and prove its correctness. And so we found a lot of corner cases in compilers. In this process, we discovered that even when compilers don't want to do anything with floating point, they get floating point optimizations wrong. So a simple bug that has been lurking around in a mainstream compiler for 10 years was it was flipping the sign of 0. And William Kahn has a fantastic paper on how it causes issues with branch cuts. So we got excited about it. We reported the bug. It was fixed immediately. And then compilers have this amazing mode called as the fast math, where it treats any identity with real numbers as an identity that holds with floating point and optimizes the program. For example, associativity. Associativity is not true with floating point, but like it treats associativity as holds and parallelizes the code. And you may think like, how does it matter, right? So it turned out like I had a fantastic student who trained a neural network, again, a custom neural network. And all he did was he trained it with fast math and trained without fast math. The accuracy without fast math was like around 89%. And then we ran, all he did was change the rounding mode, ran fast math, the accuracy dropped to 25%. And then we wanted to debug what the hell is happening, right? So how do we go about debugging? And there are no tools available. So then we decided, okay, let's build a shadow execution framework where we take the original floating point program. This is the training, the model, the training infrastructure for the neural network. And I ran it with a high precision version of the same program. So we would simulate like a high precision version with the MPFR library, and we would compare the results lockstep at every step. We wanted to figure out where the error is occurring, and then how this error is getting propagated. To our surprise, we found math libraries where the instances where the two programs were divergent. So what are math libraries? These are elementary transcendental functions, e power x, ln of x. So you may say, Okay, so it's 1 alpha error or 2 alpha error, who cares, right? So in our case, like we took the same program, we started debugging on an Intel machine, and then on a GPU to accelerate it, the results are completely diverging. This was the issue that John was just mentioning in his introductory note, right? So it was like you couldn't reproduce the errors. It was like a debugging nightmare. And then on, what would happen is this small rounding error would get amplified with catastrophic cancellation. And then you would have branch flips. Your program would take different branches compared to an Oracle execution. You would have slow convergence. And the worst of all, you would get nans and infinities in your program. And then like once you get nans, like everything gets poisoned and like you have total weird results at that. So this is where my foray into elementary functions started. So I wanted to understand, okay, how are people designing elementary functions? And why are they not producing correctly rounded results? So I want to emphasize here, IEEE 754 standard mandates correct rounding for primitive operations, addition, subtraction, multiplication, and division. It does not mandate, it recommends correct rounding for elementary functions. As a result, like no one implements correctly rounded elementary functions. Okay, so now I've been talking about correct rounding. What is correct rounding? So let's look at a number line, a real number line. So there are infinitely many points, right? So only finitely many of them are representable with any finite precision representation. Like let's say floating. So here V1, V2, V3 are values representable with floating point. Okay. So now you compute a transcendental function with the best state-of-the-art algorithm, and it produces a real value. And in most cases, it won't be exactly representable in your floating point representation. And then you need to round it. So generally, there is a rounding mode associated with most representations. So the most commonly used rounding mode is round to nearest, I goes to equal, right? So now when you round this real value according to the rounding mode, you could get V2, which is the value that is representable in your floating point representation. This V2 is the correctly rounded result. Let me emphasize, you compute the transcendental function with real arithmetic and you get a real value. And finally, you round it according to the rounding mode and you get a value in the floating point. This is the correctly rounded result. Okay. So now, how do people approximate this correctly rounded result? So as we are talking about real arithmetic, people use classical results from approximation theory. So Weierstrass approximation theorem and Chebyshev's approximation theorem. They all say like how to approximate the real value of a continuous function. Okay, so everyone approximates the real value of f of x. And now, like as you can see in the figure, like you can only do this approximation very well if it is over a small domain. So if your domain is the entire floating point domain, the dynamic range, that is like minus 2 power 149 to 2 to the power of 128. So no approximation is going to work. So you can do approximation effectively over a small domain. So you need to reduce the domain of the function. And this is called as range reduction. So what do? You have an input over the entire domain, you reduce it to a small domain. In the case of LAN function, you would want to reduce it to 1 to 2, let's say. So you reduce it and then you would invoke results from approximation theory. One classical way to approximate over a small domain is a mini-max approximation. What are you trying to do? You're trying to create a polynomial that minimizes the maximum error across all points. Okay, it's classical results, like they're fantastic results from it. And then you would generate the result, the polynomial, you do the polynomial evaluation over the minimax polynomial that you obtain, and then you would compensate it to produce the result for the original input. So effectively, there are 3 steps, right? First, you have range reduction, which reduces an original input to a smaller domain. And then you have polynomial approximation, a minimax polynomial that is generated. You evaluate the minimax polynomial over the reduced input. It produces the output for the reduced input. And then you compensate the result to produce the result for the final, for the original input. So this range reduction, polynomial evaluation, and output compensation typically happens with some finite precision representation, which is you want it to be supported by hardware. So let's say a double or something that is natively supported in hardware. Okay, so now why do these approaches produce wrong results? Okay, so let's consider a result of an elementary function which is very close to the rounding boundary. Here, v1 and v2 are two adjacent points with respect to this blue dot, which is the real value produced by an elementary function. And this the real value of the elementary function is very close to the rounding boundary, which is the midpoint of v1 and v2. So now the amount of freedom that the minimax polynomial has is shown in the gray bar on the slide. Since it's very close to the rounding boundary, this is the maximum freedom that you have. Now you need to generate a minimax polynomial with extremely high amount of accuracy. So alternatively, what typically happens is the minimum error generated by a minimax polynomial is more than the amount of error threshold that this input can tolerate, and this results in wrong results. Further, you're implementing range reduction, output compensation, and polynomial evaluation in some finite precision representation. So it's going to have numerical error. So it may cause the eventual result to be slightly beyond the amount of toleration that you have for this input. As a result, you get wrong rounding. Okay, so if you're designing a math library, what do you want to typically produce? You want to produce a correctly rounded result. So one of the key insights of the RLIBM project was we want to produce correctly rounded result. Why are we worried about the real value of the transcendental function? Okay, so John was alluding to table maker's dilemma, right? There are two main challenges in producing correctly rounded results. One, having an oracle that tells you what should be the correctly rounded result. And this is what table makers, like, you don't know how much precision you need to evaluate like your algorithm to produce the correct result, right? Especially when you have a value that is very close to the rounding boundary. And then if someone gives you an oracle, how do you actually generate an approximation that is fast and still produces the correctly rounded result? So one of the insights that we had from John's paper, Minefield Method, was, okay, so your goal is to produce correctly rounded results, approximate the correctly rounded result directly. So this requires us to have an oracle. In our case, like, we use MPFR libraries, which is simulated with 22,000 bits of precision as our oracle. We use those algorithms, produce the oracle. Once you have the oracle, our goal at hand is to produce an elementary functional implementation that is extremely fast and produces the correctly rounded result. Okay, this is the first insight. Like, if you want to take away three things from the top, the first thing I want you to take away is, if your goal is to produce correctly rounded results, directly approximate the correctly rounded result. Don't use real value as a proxy to generate the correctly rounded result. Okay, so now once you decide to approximate the correctly rounded result, there is an interval of real values around the correctly rounded result. You produce any real value around this interval, it rounds to the correctly rounded result. This is the maximum amount of freedom that you have to produce your polynomial has to produce the correctly rounded result for this input. And what we show in our papers and in the project is this freedom is much larger than whatever you typically get with a minimax polynomial. Okay, so if you approximate the correctly rounded result, you have a freedom, which is like the rounding boundary that produces this exact result, right? So that is the total maximum amount of freedom. So one thing you need to do is you still need to take into account, when you compute this boundary, any error, any numerical error that may occur with range reduction, output compensation, and polynomial evaluation. So adjust the boundary. So the first thing that we do is we approximate the correctly rounded result. Once you approximate the correctly rounded result, there is an interval of real values around this correctly rounded result. You produce any value in this interval, it produces the result that you want. So now what is our algorithm for it? You have an elementary function, you have a representation of interest and a rounding mode that you are targeting. For every input, use an oracle to produce the correctly rounded result. Okay, so all we are doing is like we are using an oracle. So we are not solving a table maker's dilemma. You're just punting the table maker's dilemma onto the side. Like, let's someone solve the hard problem. So what we are doing is like, we want people to use correctly rounded results. So use an oracle and identify the correctly rounded results. But why can't you just use MPFR correctly rounded libraries, right? Because they're very slow. No one wants to wait like 2 hours for your neural network to just give a single answer, right? So you want fast libraries. So this is the goal of the RLIBM project. Now you have a representation, you have a function, you have a rounding mode. I use an oracle, generate the correctly rounded result for all inputs. And then what do? Identify the rounding interval corresponding to the correctly rounded result for each input. Okay. This rounding interval is the freedom that you have for the polynomial. So what should the polynomial do? When you evaluate the polynomial on a particular input x1, so it has to, if the interval is L and H, like the lower bound is L and higher upper bound is H, the result of the polynomial has to be such that it's greater than L and less than H. So now how many constraints do you have? You have as many points you have on the in your representation, right? So it's a system of linear inequalities. Okay. So now what are we trying to do? We are trying to solve for a polynomial. So what is a polynomial? It's C0 plus C1x plus C2x squared. Then what are x's? X's are input points. So what we are looking for is to find the coefficient of coefficient C1, C0, C1, C2, the C on, CD. In the case when the D is the degree of the polynomial. So this is a system of linear equations, like, and there are like amazing LP solvers out there, just use them. So again, there are like, you have billion constraints, how do you solve them? No LP solver can handle them. So, but the key observation is, this is a linear program of small dimensions. You have lots of constraints, but like very few variables. We have a clever algorithm. We can talk about it after the talk if you're interested. So what have we done? You approximate the correctly rounded result, and then you have an interval of values around the correctly rounded result that imposes a linear constraints on the output of the polynomial. Now we have a system of linear inequalities corresponding to every point in your representation. Solve this, you get the coefficient. And there you go. So since you have the largest amount of freedom compared to any approximation that you could do, the resulting polynomials are very fast. Okay. So if all you had was one representation, one rounding mode, the world would have been so good, right? Like now you have results, you have like functions in math library. Let's produce all of them. But unfortunately, like floating point performance, or like any approximation, like Posit or bfloat 16, like any approximate, people are designing new representations to approximate real numbers, and their performance is amazingly important. So one of the questions is, how do we generate? Like, we don't want to be generating like new math library for every representation and every rounding mode, right? So from a library designer viewpoint, like you are the maintainer of libc, you don't want like 20 different functions for every, because like once the code is there, like it's always there, like identifying what it does 20 years hence is going to be very difficult. So and people are designing new representation. Posit is one example. Like there's bfloat 16, the TensorFloat 32 was just proposed. Like it's a 19-bit representation, like it's a couple of years ago. And then there is Microsoft has this MSFP, which is a block floating point representation. Then there is FlexPoint from Intel. Like everyone is designing new representation. So it's a great time to be thinking about numerics because performance matters, right? So our goal is, can we design a single polynomial approximation that produces correctly rounded results for multiple representations and multiple rounding modes? And this research, we have been working on the RLIBM project for like 2 years. And one night, like John sends me a note, oh, I want to mandate correct rounding for posits. Can we have a single polynomial approximation that works for like multiple? Like let's make like posit 32.2 to 8.2 the common way to change the precision of the posit representation. That got me thinking, and then we started looking at like why is it hard to produce a single elementary function, single implementation that works for multiple representations? So we all know like there's a 64-bit libraries out there, right? Like CRLIBM is a correctly rounded 64-bit math library. So why don't we just use it to produce correctly rounded results for like bfloat 16, which is 16-bit representation or a 32-bit float? So let's say we are looking at log 2 of x, which is a elementary function, and then we wanted to produce a result for a 32-bit float. We don't have a correctly rounded float library. We could take the 64-bit library that is available from CRLIBM. You have your input in the floating point representation. You convert this into double, okay, and then you call the CRLIBM or any of the available libraries. You get the output of the library in double, and you round it back to float. So unfortunately, it turns out that you don't get correct results for all inputs. Yeah, it may be close enough if your library has reasonable amount of precision, but it will have wrong results. And this is due to double rounding. Okay, this is the double rounding error. So what is double rounding? So in the bottom of the slide, I'm showing you the representable points with a double representation. Again, like this is not according to scale. Double has a lot more values compared to floating point. I can't plot all of them. This is for illustration purposes. So you have an elementary function. The star indicates the value of the elementary function in reals. Okay. So let's say we are looking at a correctly rounded library. The first rounding occurs when the double library rounds the real value into the double representation. Okay. So the first thing to note is this real value is less than the midpoint between the two floating point values you have in the second row. Okay. But when you did the rounding, first rounding, you lost this information. When the value is very close to the rounding boundary, you lost that information. When you round this double value back to float, you rounded it wrong. Rounded it to a wrong result. And what is the wrong result? Like if you had taken the original real value and directly rounded it to using the floating point representation, you would have rounded it to the blue dot. So this is the double rounding error. So we want to avoid, if you're going to design a generic library that works for lots of representation, you want to avoid double rounding error. Okay. So and what is our key insight? So when you do to avoid double rounding errors or to avoid wrong results in the presence of double rounding, when you do double rounding, it has to maintain enough information about the original real value. So what is required for rounding? Typically, if you're doing let's say you're rounding with respect to two adjacent floating point values, you need three pieces of information. One, is the real value less than the midpoint of two adjacent values? Is it exactly equal to the midpoint? Or is it more than the midpoint? If you have these three pieces of information, along with the adjacent to floating point values, you can do correct rounding. So our key insight in the RLIBM project to make that allows us to design correctly rounded libraries for multiple representations is based on this observation that if you want to avoid double rounding error, preserve this information. Okay, so let me tell you like the high-level sketch. So if you want to create a correctly rounded library for a representation with n bits or lower, okay, or with any rounding mode that is recommended by the standard, like let's say in this case IEEE 754, 5 rounding modes. So then create a correctly rounded math library for an n+2-bit representation with the round to odd mode. So this is a non-standard rounding mode, which I'm going to describe. So let me repeat the insight again. So if your goal is to generate a correctly rounded library for a representation with n bits or lower, with any of the 5 rounding modes, create a correctly rounded library for an n+2-bit representation with the round to odd mode. So what is this round to odd mode? The round to odd mode is not new, actually. Like we found instances of it in the seminal Goldberg paper from 1991, when to avoid double rounding. So Goldberg wanted to convert a decimal fraction into a binary fraction, and he wanted to avoid double rounding errors, and there's an indication of round to odd. And similarly, Sylvie Boldo and et al. Have like a couple of papers on how to do extended precision arithmetic while avoiding double rounding errors. Okay. So if people have already done it, why didn't anyone design a math library with round to odd? So this is because if you're doing mini-max approximation, it's extremely challenging to reason about error in the context of round to odd. There's a lot of numerical analysis work with round to nearest ties to even, but people have done like seminal progress on it. And since people have been focused on round to nearest ties to even, and they've been primarily focused on mini-max approximations, they did not discover this insight. So our observation was, how do you construct correctly rounded elementary functions for multiple representations using this insight? So if you want to, you can probably apply the same thing with mini-max, but it requires new numerical analysis technique, new error analysis techniques to make this feasible. In contrast, with RLIBM, we don't care about real values. We only care about the correctly rounded result. It doesn't matter whether it's round to nearest ties to even or it's round to odd. Once you give an oracle that produces the correctly rounded result, we will take that as our starting point and we quickly do it. So this is the key reason why we have been successful in generating a single polynomial approximation that works for multiple representations. Okay, so now let me tell you what is round to odd. So round to odd can be described in 2 sentences, right? If a real value is exactly representable in your representation, it rounds to that value. Okay, if a number is exactly representable in your representation, you just round to that. If the number is not exactly represented, you need to do rounding, it rounds to a value, rounds to an adjacent value whose bit pattern, when interpreted as an unsigned integer, is an odd number. Okay, so now you may be wondering, why does this round to odd work? Like that sounds like magic, right? So as I told you just a few minutes earlier, what are the 3 pieces of information that you need to do rounding? 1, is the real value less than the midpoint of 2 adjacent values? Is the real value more than the midpoint of adjacent values? Is the real value exactly at the midpoint? Okay, so now let's take a real value. We represent it with infinite precision. Okay, and you have your representation has n bits of precision. So now look at the n plus 1 bit. If the n plus 1 bit is a 0, then your real value is less than the midpoint. If the n plus bit is a 1, and all the remaining bits from the n plus 2 bit are zeros, then it is exactly at the midpoint. If the n plus bit is a 1, or if any of the bits from the n plus 2 bit is a 1, it's above the midpoint. So now we capture the n plus bit. This is also called as the rounding bit for people who design floating point hardware. And the OR, a bitwise OR of all the bits starting from the n plus 2 bit onwards is the sticky bit. So typically, to do rounding, to round a real value appropriately, you need the rounding bit, you need the sticky bit, and you need the truncated value. If you have these 3 pieces of information, you can correctly round any real value to an appropriate representation. The round to odd mode exactly preserves this information. This is why you have n plus 2 bits, and the round to mode exactly preserves the same sticky bit and the same rounding bit, and the truncated value is unchanged. And this is why this works. Okay, so now let me go over the illustration that I had, like when you took a double value and you rounded initially the real value into doubles and then to floating point, how it flipped. So in contrast, like when you do the rounding with the round to odd, you will round to an odd value. So you're preserving the information that it is still less than the midpoint. And when you round this back, it rounds to the correct value. Okay, so double rounding is inevitable because you're designing a representative. You're rounding once from real to some finite precision representation. And then you're rounding it back to a lot of target representation. So you are going to do double rounding, irrespective of whether you want it or not. But what round to odd ensures you is, even when you're double rounding, you're not losing information about the original real value. And that was like our insight. So I'm giving you a high-level sketch of what the insights are. The mathematical proofs to show it works for every rounding mode is a bit involved, like our papers provide you all those proofs. Okay, so now what our proofs show is this will produce correctly rounded results for multiple representations. Okay, We have shown it, and there are some caveats which I'm going to display. So now, what is our algorithm to generate correctly rounded results for multiple representations? It's similar to the original thing. So for each float input, we are going to compute the correctly rounded result, but now with the round to odd mode. Okay. So the elementary function in question is log2 of x, and we want to do it. We want to produce correctly rounded results for multiple representations, starting from 32 bits to 10 bits, and we compute the correctly rounded result of log2 of x in a 34-bit FP representation. Okay, and now we compute the rounding interval, which is the say interval of real values, such that every real value rounds to this correctly rounded round to odd result with a 34-bit FP representation. So it's the same thing as we had before. The only thing is now the rounding mode that we are using to generate the correctly rounded library with a 34-bit representation is round to odd. So the one thing you will notice with round to odd, if the elementary function produces an output that is exactly representable in the n+2-bit representation, in this case 34-bit representation, and its bit pattern is even, then the rounding interval is a singleton. Okay, so now doing polynomial approximation with singletons can be extremely challenging. Okay, so why? Because like the polynomial does not have a lot of freedom. So what do? So what is a floating point output, or what is a floating point number? It is a rational number, and you have a transcendental function which is producing a rational output. We want to filter them so that like our polynomial in approximation has a lot of freedom for the remaining inputs. So this problem of identifying rational output, identifying rational inputs of elementary functions that produce rational outputs is well studied by Weierstrass and many others. So we use the results to identify all inputs for which the output of the elementary function is a rational value, and its bit pattern is even. Okay, so in the context of log2 of x, when do you get a even result? When do you get a rational result? Whenever the input x is 2 to the power of 5, and I is an integer, I is an even integer, I is an even number. So because we want like log2 of x, the result is exactly representable in the representation and should be the most bit pattern should be even. So we can identify this initially by catching them, and then we can produce the correct results using bit vector operation. Like computing 2 powers is very easy, so you just use some shifts and you produce the result. And what you are remaining with, what you are left with, is the set of rounding intervals for the round to odd. Now use the exact same LP formulation that we had, generate the polynomial, and this polynomial produces correct results for all representations starting from n bit to e number of bits, where e is the exponent of the representation that we are looking at. Okay, so what are the 3 things I want to take away from this? Now, first, if your goal is to produce fast and correct math libraries, and you have an oracle, so then approximate the correctly rounded result. Okay, and once you decide to approximate the correctly rounded result, there is an interval around this correctly rounded result. That is your freedom. Now we use an LP. We frame this problem of generating polynomials as a LP problem, a linear programming problem, and we use state-of-the-art linear programming solvers, and there are like amazing results by others to solve linear programs of small dimensions. We use that and generate polynomials. There may be other ways to solve it too. So yeah, and what the bottom line is, this freedom by that you have by obtaining correctly rounded result is much more than whatever you get from a mini-max polynomial. And now, if you want to generate a polynomial approximation that works for multiple representations, and your the biggest representation that you're looking at has n bits, create a correctly rounded library for n+2 bits with the round to odd mode. And if you use the RLIBM approach, like approximating the correctly rounded result, it's straightforward out of the box. One thing you need to pay attention to is the issue of singletons. And that you can consult any approximation theory book. You have fantastic results and you can do this. So what we show both mathematically and empirically is this produces correctly rounded results for numerous representations. Please see our paper or talk to me by email or during the Q&A for the details about the proof. Okay, so does it work? All this is like nice fiction, right? At the end of the day, like what developers care about, give me a library that is fast and is also correct. So what we have done is we have generated a set of 10 elementary functions that produce correctly rounded results for all inputs, such that your representation has at least 8 exponent bits, and for any fraction number of any fraction bits ranging from 1 to 23 bits. So there are 23 bits. You have freedom. You can choose 1 fraction bit and 8 exponent bits, 2 fraction bits and 8 exponent bits, or 1 exponent bit and 3. You can experiment with it. So there are 161 such configurations, which also includes a B float, 16, tensor float. All those come under this permutations with the exponent and the mantissa that you can play with. And there are 5 rounding modes in the IEEE standard. Like when you multiply them, there are 805 different configurations. A single polynomial approximation that produces correctly results for 805 different rounding modes for all inputs. So this was like fantastic. Like we were like really excited, and we pushed this. Now, like this is not just like a prototype code that we maintain on GitHub, right? With assistance from LLVM developers, now LLVM's libc uses correctly rounded functions generated by our approach, and it produces correctly rounded results for all 5 rounding modes in the IEEE standard. So again, not everything. Right now we have pushed 3 functions: ln of x, log2 of x, and log10 of x. Okay, so now this is fantastic. Like you have correctly rounded results. Is it fast? Okay, and how does it compare to other libraries? Like first of all, let's look at our competition, right? Take Intel's glibc or Intel's libc. Take glibc's liban, and even look at CR-liban. So all these produce wrong results for either some rounding mode or some representation. So the point to note is like CR-liban is a correctly rounded library. So a lot of people have invested a lot of time in developing them. So for doubles, for round to nearest, they produce correctly rounded results for all inputs. And they have different polynomial approximations for different rounding modes, like 4 distinct polynomial approximations for 4 different rounding modes. So when you just take them and round it, you still produce wrong results. This is due to double rounding. So in contrast, like if you're all you care about is 32-bit floats and the precision lower than 32-bit floats, you can use RLIBM and its functions. It provides you correctly rounded libraries. The next question that you may ask is, how much are you paying for this correct rounding? Is it fast? Okay. So in this slide, I'm showing the speed up of RLIBM functions compared to Intel's float functions and Intel's double functions. So since we are talking about speed ups, higher bars are better. Okay. So a line of 1.0 means our functions and Intel's functions are exactly the same. And we are using performance counters to actually measure the number of cycles. So if you look at like Intel's float functions, we are on average 30% faster than Intel's float functions. And Intel's float functions does vectorization, does a lot of sophisticated things to get this performance. Okay, and moreover, it produces like more than 100 million wrong results with about 1 to 2 alpha. So in contrast, we are faster and we are correct. We are correctly rounded. Our error is less than 0.5 alpha. And when we compare to double, Intel's double functions are a bit more accurate compared to its float functions. Compared to doubles, we are about 50% faster. And Intel's double functions are also produce wrong results due to double rounding errors. Okay, so in summary, we are faster than Intel's functions. And again, I don't want to take too much blame, right? I think this is the beauty of the idea here. So it's just 3 of us, like me, my student, and my collaborators working on it and building it. And Intel developers have invested years and years of work to generate this pretty good implementations. the fact that we can generate fast and correct libraries shows like the merit of the idea. So again, we are not solving table maker's dilemma. You're using the Oracle and generating fast implementations. Okay, so now you may be wondering, now if my goal is to look at correctly rounded, like how do you compare to CRLIBM? CRLIBM is a correctly rounded library for the double precision. Compared to CRLIBM, we are almost 2x faster. So part of it is because like CRLIBM is designed for double precision, so they need more accuracy, so they spend a lot of time optimizing it. So and CRLIBM, when you repurpose it for flow, it produces wrong results. Okay, so hopefully by now I have convinced you it is feasible to generate fast and efficient, correctly rounded elementary functions. Okay, so even if you like slept through the entire talk, 3 things I want you to take away. One, if you don't want to tackle the hard problem of generating efficient oracles, so use an existing oracle and then approximate the correctly rounded result. Once you do that, you have a lot more freedom. You have an interval, frame it as an LP problem, you get really efficient polynomials. Then, if your goal is to have a generic library, one library that works for all, right? So then generate a correctly rounded library for n+2 bits with a round to odd mode. It produces correctly rounded results for n bits and lower. Okay, so I think it's high time we revisit correct rounding in the standards, at least for representations up to 32 bits. There is no reason why we should not be mandating correctly rounded results for at least representations up to 32 bits. So what does it take to do it for doubles? That's a research question. And as an academic researcher, I'm exploring it. When will we succeed? I don't know. So that's the luxury of being an academic, right? So all our prototypes and papers are available. And you can also see the conversation that we had in pushing these libraries mainstream with libc. Again, this is in collaboration with Paul Zimmerman from INRIA and Google developer Theo Lee and various others. Like, again, there is a nice community of researchers and practitioners who want correctly rounded libraries. And if you are interested in contributing, please get in touch with us. And finally, I want to thank National Science Foundation for seeing value in this work and generously funding both me and my student to pursue this line of. And thanks again for your attention. And I hope I convinced you that correct rounding is both feasible and can be made very fast.
Thank you very much, Santosh. I don't know if we applaud over virtual meetings or not, but excellent talk, fantastic. I had a number of comments I want to get in, but we also have some questions from people. Paul Leopardi, let's take him first. He says, what are the prospects for correctly rounded matrix singular values or eigenvalues? Is anyone working on this?
So I don't know at the top of my head. So, okay. For example,
I will tell you that I am. Yes, but it's a different approach. It uses the quire. That's how you can get absolutely correctly rounded solutions to AX equals B or QR factorizations or anything you want to do. It is possible to do them accurate to the last bit using the quire to verify the result. That's a kind of a completely different approach from yours. He also asks, have you considered Padé approximation versus polynomial approximation? What is the trade-off?
So we have been starting to explore Padé approximations. And even like changing bases so that like some of the approximations are better. Like again, like you've only done 10 functions, right? For Bessel functions, for example. So we would have to look at, like, carefully investigate other kinds of approximations. Again, yeah. So
yeah. Will that fit into your linear programming framework, though, if you have to choose between using a polynomial or a rational function? Because the Padé approximation.
So for now, like we have been stuck with polynomial approximations because like one of the things that we use is a high precision linear programming solver. But like that is, as I said, it's just one idea, right? Like you could, you have a set of constraints which may be richer than just like linear constraints. So then you can use different solvers. And there is like fantastic work in various convex solvers and non-convex optimizations. So we could use that. So those are all like again, we have been working on this for 3 years. So,
Mhm.
so it's not like a lot of time that we have spent on this.
Sure. I recommend you try it on the tangent, because whenever I've done a math library, cosine and sine are natural for polynomials. As soon as you hit the tangent function, you say, you know, I can get away with a lot fewer coefficients if I just make it the ratio of these two things, which is, of course, where the tangent comes from, is that sine over a cosine. But you can see that in the, you know, the very steep rise of the tangent. It just is a natural for that. I've got a question, or actually a statement from Stefano. Brilliant talk. Linchpin question. The model depends heavily on the quality and speed of the oracle. Can you give some insights on the efficiency of different oracles you tested?
So we have been primarily using MPFR as our oracle. So what we do to check it is like we run it with like, we have run like generated oracles with 10,000 bits of precision using the MPFR algorithms, 200 bits using the MPFR algorithms. And they produce, like, when they agree, that is how that is what we use as the oracle. And again, so we that's our trusted computing. We're not like designing oracles. Like, our goal is someone gives us an oracle, then we work on it.
By the way, I use Mathematica for my oracle and when I'm doing applying this method, but there is a French effort. I cannot remember the name of the fellow who did it. I think it's University of Lyon, to table all of the hard to round points and publish them.
Vincent Lefebvre.
That's it,
Lefebvre.
Vincent Lefebvre. He's made a project. I don't know how many years it's been now, maybe a decade, to say here are the functions where it just happens to land very, very close, you know, to maybe more than 10 bits, almost exactly halfway in between. Once we have all of those tables, we have a true oracle. You can put it up on the web, and you don't have to compute. You can just go look it up and say, for this precision, I'm going to have trouble with this point, and this point. And those are the constraints that you worry about. So you don't have to go through 4 billion calculations of an oracle function. You might just have to look it up. It doesn't take that long to find out where these points are.
So MPFR libraries actually do that. So they, we are from Vincent's work, it has been shown that you can approximate, like, if you use the MPFR algorithms with like 300 bits of precision, it produces the correctly rounded result for floating point representation. So these are the results that we rely on. Again, we trust the oracle. Like, you provide us a better oracle, we will produce you better polynomials.
Right. So the method of Ziv is what people have been doing up to now. That's where you say, I'm going to carry 5 extra bits, and if it's clear that it rounds down or rounds up, then I'll just do that. But if I can't tell, then I'll redo the calculation using quadruple precision or octuple precision. And you might have to do the calculation several times. And what this leads to is a very uneven speed. Maybe you're fast for most of the functions, but every once in a while you hit one that takes 100 times longer. And my experience is programmers do not like it when something surprisingly is data dependent to that kind of orders of magnitude slower, just because you hit a hard to figure out number. So the Ziv method is really obsoleted by what you've done. I also have to put in. Go ahead.
So it's called as the onion peeling strategy. That
yes, the onion peeling. Peel the onion. Keep getting deeper. I believe your libraries have been hooked up. I don't know if our next talk is going to touch on this, whether Theo Omtzigt has applied your libraries, but I do know that Serlaine Leong has attached a branch of her GitHub so that soft Posit can hook up to your libraries. So you can get not only plus minus times divide and square root, but you can also hook into all the elementary functions you would need for, well, a large subset of the GCC math library or any other C type math library. So that's already been adopted. I wondered, is Intel or GCC going to use your method? How can they not use it?
So I think like LLVM's libc, which is a new effort to create a new correctly rounded library, which involves like buy-in from GCC, LLVM, and various industrial developers. So they are building it, and we are contributing to it. This is the effort in collaboration with Paul Zimmerman and a few others.
Great. Well, that was great. Thank you again for an outstanding talk. Yes. So we are now right on time for our next talk, which is Dr. Theo Omtzigt on Universal, reliable, reproducible, and energy efficient numerics. Dr. Theodore Omtzigt is a leading expert on the use of advanced analytics to create intelligent systems. He is the inventor of the domain flow programming model and the distributed data flow execution engine for scalable, high performance parallel computation. He's designed and constructed many industry firsts, from autonomous learning, design systems, to diagnostic processors and high volume consumer products, to the first trillion triple semantic database. When I talk to him, I can't figure out whether he's a hardware expert or a software expert. He seems to span the entire range, a really incredibly smart guy. So let's hear about Universal, reliable, reproducible, and energy efficient numerics. Theo?
Thanks, John. And to answer the question, we are pulling in RLIBM, but we still have that question, like in the library, we can do configurations that would break the linear programming model. So Santosh knows our problem, that we would like to have math libraries for 128-bit floats or posits, right? And that is still something we're trying to figure out how to at least make a stab at it. But yes, we are definitely bringing RLIBM into the work that we're doing with Universal. All right, well, on that note, good morning, everyone. The talk that I have prepared is a quick update, a status update on the progress that we've made with Universal version 3, which was developed over 2021. In 2021, we're about to cut the start for V4. But this is joint work with James Quinlan of the School of Mathematical and Physical Sciences of the University of New England. And let's see if I can move this forward. Yes. All right. So why Universal? Universal started in 2017 as a hardware verification library for the Posit number system that John was proposing. We wanted to build different hardware ALU systems and generators for it, so we needed a reference implementation. So Universal started its life as a hardware verification library. But as we were sort of working with integrating these posits into different application programs, you always got the question, well, how does it compare to my fixed point implementation? How does it compare to a double implementation? So we sort of very quickly got presented with this problem that you need to be able to compare different number systems, because if you're doing number system research, you are typically comparing the cost and benefits of different implementations or different representations. So as we were sort of working on this, the places where people were very comfortable with using new number systems were either the high performance computing folks that were trying to tackle reproducibility, or the signal processing folks that were building embedded intelligence applications. On the high performance computing side, it was always reproducibility. That was the differentiator that people were trying to solve. On the signal processing side, it was always sort of energy efficiency that was the case. So, for example, John mentioned in his introduction that posits are being used in 5G. When we presented the first incarnation of Universal in 2018, I think it was, the Supercomputing conference in Denver there, we got our days filled with trying to explain to Huawei engineers how posits worked. and they were trying to solve the problem of dynamic range over their fixed point implementations. So these are examples where people sort of recognized in the signal processing space that if you're starting to implement bigger algorithms such as multiple in, multiple output type beamforming and these type of things, where suddenly you're doing a lot more computation for which that fixed point representation that your original signal processing was used for is no longer cutting it because your computation demands higher dynamic range. Posits were a very, very easy shoe-in to be able to present that. So we're seeing this quite a bit now, where the high performance computing folks are to some degree somewhat constrained by the hardware that they have, whereas the IoT and the embedded intelligence communities is innovating every single day, and 9 out of 10 times that happens with custom arithmetic. And that is really easy to understand, because if you sort of think about what has been proven, it's been proven that measuring behavior of a complex dynamic system and then trying to predict and optimize that behavior, that is very valuable from a commercial perspective. And this has clearly been demonstrated in all large-scale industrial process control systems, where that optimization process can lead to very high efficiency improvements. But it has been commoditized actually over the past 20 years through media, and particularly advertising and e-commerce applications, right? So the Googles and the Amazons of the world, they are streaming billions of events through their systems, and they are definitely leveraging the predictive and the optimization aspects of these. Now, if you want to drive that same optimization process into physical systems, then you somehow need to really get these physical processes is instrumented, and that requires sensors of some kind. And if you sort of think about instrumenting a physical process, you tend to have hundreds, if not thousands, of instrumentation points in order to really understand how the system behaves. And that can only happen if you have very low cost. So these low cost sensor is the driving force behind sort of the digital transformation that we're seeing in the physical IoT spaces. And these are all governed by custom arithmetic these days, because they have to be energy efficient and they have to be low cost. So if you then extrapolate to sort of the systems that use the sensor data, you basically see structures take place where they aggregate the sensor sampling, measurement, prediction, signal processing, and decision making that then drives actuators in order to manipulate the physical environment. So these embedded intelligence systems basically bring all of these pieces together and place them really in the physical processes themselves, particularly around the sensors. The actuators tend to be a little trickier because they tend to be high energy type systems. But particularly on the sensor side, smart cameras are a great example. You see this integration of sort of the sensor, the signal processing, and then the perception pieces all sort of being integrated into the same spot. Now, the first signal processing stage is typically done today with deep learning type approaches. And then the decision making and planning pieces tend to be driven and constrained by constraint solvers. And both the deep learning and the constraint solvers are really compute intensive. And therefore, if you try to meet the energy requirements for these embedded systems, the only way you can really do that is by creating specialized accelerators for either the perception task or the sensor fusion task. And if you do decision making, you need to do sort of a least square or some other type of constraint solver in order to be able to find these systems in an energy envelope that fits the embeddedness. So basically, in summary, these systems really are being constrained by their power consumption. And the only way you can really get to that, because of the intensity of computation that takes place in the deep learning or the constraint solver, forces you to use custom accelerators. And if you do that, then you immediately have an opportunity to drive your energy down by using custom arithmetic. So if you then sort of look at what the microarchitecture setup of these systems will be, you see that there still is an important integration or collaboration between some sequential control flow and these hardware accelerators that are optimizing these particular steps in the pipeline for energy efficiency. And the handshake between these two devices, the sequential processor on the one side and the hardware accelerator on the other side, is most naturally done through memory. But then you have data structures that allow you to set up these hardware accelerators so that they're efficient. And that handshake between the CPU and the accelerator tends to be structured either through some tensor or some vector streaming type sensor streams. So the CPU and these accelerators really need to collaborate. And if you're going to use custom numerics, then you have this problem that there is a layer that the CPU sort of needs to be able to support. 9 or 10 times it does not support the custom arithmetic that the hardware accelerator uses, but the CPU is still asked to manage, set up, and sometimes transform these data structures. And therefore there is this layer that is necessary where the CPU can actually do that on behalf of these hardware accelerators. And fundamentally what the third edition of this universal library has come to is to provide the services that make that easy. All right. So the way that works is, given the fact that Universal is a library that has tens of thousands of number systems, arithmetic types that approximate number systems, it provides a software emulation layer that the CPU and even a GPU or any other type of device, computational device that can manipulate integer math really, will be able to interpret and compute on these arithmetic types. So the CPU now is able to manage all these data structures, potentially set up a Posit tensor on a deep learning network, or a B-float matrix coming from some Onyx setup, or as we're seeing now more and more, particularly in the deep learning space, logarithmic number systems. And the CPU is now fully capable, because the Universal extends that environment with all these arithmetic types, to set up the data structures for the hardware accelerators. So the hardware accelerators don't have to do the conversions that can all be done natively in setup time by a central processor. And this pattern that the CPU and a hardware accelerator collaborate through this memory handshake, we call sort of a universal design pattern, for which the libraries has native facilities. So let's see. So the rest, or at least the piece that is coming up now, is sort of to give you a quick sense of the universal library, the arithmetic types that we have and provide, and the things you can do with it. So the obvious sort of first step is to think about how we cover the number systems out there. So as we all know, number systems and algebraic sets are abstract concepts. Anything we do with an arithmetic type is sort of an approximation of these algebraic sets. And it's particularly in the energy efficiency trade-off that you really have to pay attention to, particularly size and encoding efficiency. So the cover for basically from natural languages all the way to the reals you can sort of quickly see you got your decimals and the integers on the natural number side. Then you got your fixed points and rationals for your Q, and then the approximation of the reals, your regular floats, your posits, and then you have logarithmic number systems. And then we have some interval pieces in the form of reals, which are A reals are faithful classic floats with an uncertainty bit. Valids are, of course, an interval arithmetic with posits and an uncertainty bit. And the unims are this variable, well, it's a fixed max size, but variable mechanism. And the reason for that is really to be able to offer sort of the progression that that John's book, The End of Error, went through. It's very much in sort of an implementation and support for that pedagogical aspect of introducing people back to these number systems and the tricks that people were playing with that have been lost to the ages, right? This was very common. I think it was von Neumann who said is that, you know, every mathematician knows how to do fixed point in their head, right? Well, that skill has long since lost. So we're really trying to bring a full practical environment in which people can get exposed, new graduates can get exposed to all of these sort of folklore and detailed and very empirical insights that these number systems brought with them. All right, so let me quickly set the stage here. Is that what we're trying to do with Universal is have basically plug-in replacements for the native types in C++ languages. And given the fact that most language environments will have a C linker interface, we can use Universal with a C linker stub to basically extend any of those languages with these arithmetic types. So we're doing that for Python. We're looking at Julia, and we're looking at Rust and Golang stubs, so that all of these languages will have access to these arithmetic types. Then the Universal library is fundamentally a C++ native library. It's a header only, so there are no compiled pieces. You bring in a type simply through an include header, and then you can use that type. And then the parameterization that we're using is really as fine-grained as individual bits to control the size, and individual bits to control exponents or ranges or bases, whatever number system you're interested in. So we're typically parameterizing in precision and dynamic range, but then we're also specializing on arithmetic behavior. So number systems can be modulo, or they can be saturating, or they can be clipping. And then the last piece, of course, is the sampling profile. You know, are you a regular floating point? Are you a fixed point? Are you a posit, a tapered floating point? Are you a logarithmic number system? So those are sort of the parameterizations that are pretty standard for all of the types within Universal. Then one piece, as I indicated earlier, we really got started with posits, and part of the posit standard is the support of a fuse dot product. So the fuse dot product is really an operator that we sort of offer in all its glory for all of the number systems. And the reason that that is so interesting is that the fuse dot product really is sort of a mechanism for user-defined rounding, particularly for linear algebra. And it's an incredibly powerful tool, known to the field since the 80s with Ulrich Kulich's work. So it's a fundamental building block for doing computational science. So all of the real approximations in Universal will have support for a fuse dot product. And then we have, you know, for certain add-ons, we have support for fused matrix vector, fused matrix matrix, and fused tensor operators. And then particularly in the library stuff, and the library creation stuff, there is a lot of questions about error and numerical error that you make. And we were always sort of looking for, if you try to debug something, and I'm sure that Santosh has done this in depth. When you try to debug a numerical problem, you never have enough tools. So we're sort of trying to aid in that department with support for forward error propagation type calculations, for interval type systems, and for trying to give an answer and give a statement about the number of precision bits that are still good, that have not been polluted with either tapering or cancellation. So that's sort of a broad strokes of how we approach building new types. And it's then there's sort of a bifurcation in types that are really targeting hardware acceleration, that need to be typically fixed in size and tend to be very small as well. And then we have the types that are more tailored towards the numerical and the mathematical oracle type questions. So we're on the left-hand side under the label replace are sort of the plug-in replacement types for float double, long double, and the integers. The real number systems are fixed point C float. C float stands for classic float. A tapered float, a posit, a logarithmic number system, and unum. And then we have integers, because there's also quite a few times that you need a fixed size, but still more capable than the unit types, the standard types that are in C++. Then there are these questions about reliable computing, where the computational comes in with a statement about accuracy, validity, or error. And here we have sort of the interval types. Then on the precision questions is where you really are trying to answer a question where the precision question is the goal. There we have basically adaptive precision type number systems. And the last one, the Oracle number system types, Douglas Priest's number system, and a new number system that came out last year by Ryan McCleary called Lazy Exact, where they're basically, the innovation there is that they can segment the limbs so that you don't have an infinite carry propagation. And this is really nice for, as the name sort of states, to do lazy evaluation. And then when you are asking for a particular result, to say, I would like to have this in 15 digits of accuracy. So that's a number system that we're very, very excited about. All right. So just to give you a sampling of what these types look like. Here is the simplest one, an integer type. It's an arbitrary precision, but fixed size once you've set the n bits. It's a 2's complement signed integer. And it has a user-defined block type that you can use to define the address alignment in memory. So if you are doing tensor operators with these type of types, you actually have control over how your tensor is going to lay out in memory. And this is very important for collaborating with hardware accelerators, because they may have very specific alignment constraints. So that is a parameter that is very important for that. The smallest integer you can represent is 2 bits. The largest is basically limited by the number of memory, or the amount of memory you want to accept to it. We've tested bits, integers, with a million bits. All right. Next one is sort of an approximation of the fixed point. It's still a 2's complement number, but now we have a radix bit. which basically everybody knows in number systems, a fixed point is a normalizing shift. But the type of arithmetic that you can do with this fixed point type is you can either make it saturating or modulo. So saturating fixed points tend to be very valuable in signal processing, but recently they got used by a quantum simulator, which using the saturating for probabilities. It has the same mechanism of memory alignment. The smallest fixed point you can create is a 2 by 2. So that's a full fractional fixed point. And again, just like the integer, the fixed point is only limited by memory. Now we're getting to the reals, and the first one is a classic float. It is again an arbitrary precision but fixed size classic float that is defined by its total size and this number of exponent bits. It has, from an arithmetic parameterization point of view, the ability to turn on and off subnormals. Well, subnormals we all know. It also has the symmetry when all the exponent bits are 1, which we call supernormals. So it can now also turn on super normals, which we sort of define as gradual overflow. And you can turn on and off saturation. So either you clip to infinity in non-saturating, or you will saturate to max plus if you have that turned on. It has another innovation that actually comes from the reel that John uses in his end of error book. It has a 1-bit signaling and quiet non-encoding. It has a 1-bit plus or minus infinite. So it only has 4 encodings for the special cases. It again has this memory alignment concept. It supports, or it has support for fused dot products. The smallest C float you can have is a 3-bit with 1 exponent bit, but you do have to turn on subnormals and supernormals, because if you don't turn on, then there is, there is 3 values that you have. So that would not be a very, very interesting floating point number to use. The largest ES is currently 11. As a matter of fact, 2 weeks ago, we were testing this. We can actually go up to 22 now, but there's, we really haven't done, certainly on the library side, the mathematical library side, done enough testing to really make that production worthy. All right, now we're getting into the sort of the more interesting pieces. There's the Posit. It has, again, a size and the definition of the number of exponent bits. The alignment in memory gives us the ability to use these posits in different tensor type operators for deep learning algebra, particularly. We all know that for posits, the exponential regimes are driven by that ES value as well. Posits are saturating by nature. So the only arithmetic that we really support is the min-max max plus saturating. It has 1 code for not a number, not a real, and 1 code for 0. Let's see. That's the smallest one is a 2-bit posit, and the biggest posit we have tested is 496 by 9. And my God, these are big numbers. They're fun to play with. We haven't really used them in anything productive, but they sure are fun to play with. All right, let's see. These are number systems. The logarithmic number systems are new additions, and they are really being driven by the deep learning crowd. They are undergoing quite a bit of change. NVIDIA just proposed a multi-base version. So we'll probably have to look at if we can extend this class to be able to support that as well. But of course, the logarithmic number systems are very good for providing very large dynamic range for with very few bits. and that is one of these qualities that that the deep learning folk are seeking. All right, so now we're going to go to a quick introduction to two adaptive types. Both are done in decimal arithmetic. So we have the regular decimal, and then we have the rational. So these are currently our two workhorses for doing adaptive precision type work. The rational being the sort of the workhorse for doing precision work. All right, let's see. As I alluded to, if you're going to reliable computing, you really would like to have these statements about where we believe the computation's true value lies. And the A real is a classic float with an uncertainty bit. So we are trying to give this as a first approximation for some of that reliable computing machinery. There's still a lot to be worked here because we really don't have any math library support for these type of things yet. So these are still works in progress, but that uncertainty bit is very interesting and very productive because this is a very efficient number system. When you start looking at a broader piece, the valids, which are two posits with an uncertainty bit, then you're really starting to get into serious interval territory. This also has no math library support yet, so still a work in progress, but it is something that that we would like to expand on in the next edition of the library. And then unims really, as I indicated, are more pedagogical in nature, but at the same time, we do think we're going to be able to use them for making statements about the number of precision bits in a computation without having to go through full adaptive precision type number systems. So we're hopeful that that we can do some of these things well, and that we also have some hardware support for them so that we can actually run these things at tera-op performance. All right. So that was in a nutshell the smorgasbord of number systems that we currently offer within Universal. And the library has been production worthy now for at least 3 years, and we have some good large scale high performance computing integrations. The most successful one is Gizmo, which is an isogeometric analysis package, and we're working with the University of Delft to bring the full fused dot product capability to the isogeometric piece, and particularly the sampling of space. So the Gaussian quadrature, we are trying to FDP enable that. The solvers are already FDP enabled, so that piece is already there. Posits with FDP allow for very high order methods. So for example, if you use a double precision IEEE, the order of these IGAs is typically limited to about 4. And with posits with FDP, we can get all the way up to 32. So the reason that that's interesting for HPC is, as everybody know, IGA, basically you can now have very coarse physical discretization, but you can have very deep computational demand, right? So if you look at traditional finite elements, you tend to have very high degrees of freedom because you need to sample your physical space, and then each element operation is almost nothing, right? So you're completely memory bound in traditional finite element. With IGA and posits, with 32 order splines, you're basically, you may have only 1,000 degrees of freedom, but you're completely compute bound, right? So this is a really interesting direction that that Gizmo is enabling us to research. We're very excited about that. Another implementation of integration is with MTL4 and MTL5. These are linear algebra engines, and their differentiation is that they're parameterized linear algebra, but if you give them a posit, they will use their linear algebra with FTP. So they're reproducible. And then the last one that I mentioned, or I will mention here, is LibCat. That's a quantum computer simulator, also done at the University of Delft. And the reason why that's the case, of course, is that's my alma mater. So whatever Delft needs, we provide. Anyways, the fuse dot products are very, very interesting for any type of polynomial approximation. So we're having some work with James Quinlan here on the Chebyshev polynomials. We're also trying to work on a perfect matrix inverse as sort of an HPC benchmark. MTL provides an IDR method, so we're trying to trying to study if that IDR mechanism can and combine it with FDP gives us better conversion rates for really tough ill-conditioned systems. All right, so let's see. The last thing I'll point out is on the last two on the right, the reals and the C float versus A real posit valid. We're trying to do these things in FPGA hardware so that they can be done in the cloud. So all of these number systems will have FPGA vector engines that can be deployed in Azure or AWS as hardware accelerators. And that would then give us computational platforms that everybody can use without having to worry about having to build the systems on premise. All right. The piece that I'm going to present now is the work that we've been doing with Universal. And one of the first things, of course, is the mixed precision matrix squeezing. It has been studied very, very deeply in the context of double to float to half precision for the GPUs. But typically, the study is done to do to make the condition number system or the number better for these matrices. But in this particular case, what we're trying to study is how you can squeeze without fundamentally changing the matrix itself. So the simplest algorithm, you basically clip anything that's too big, and that is not a good strategy for many systems, because on the moment you start clipping, you really start changing the matrix itself. So you have to be very aware that the dynamic range of the system that you're squeezing is going to be capturable by the dynamic range of your target number system. So people sort of know that, and given the fact that Universal has these very small number systems with very small dynamic range, this is something that rarely suffices. So the next step is to try to scale your matrices, but now what happens is you're solving the overflow problem, but you're now introducing underflow. And this is a problem as well, certainly if you are using target number systems that don't have subnormals, for example. These things then become very singular frequently. So the quick solution for that, and we're still sort of progressing in this piece, but it's to actually scale your matrices by row and column equilibration. The details are in the paper, but the research really is quite rich on the moment you start changing your profile, and we are just getting started with these pieces. So very exciting. Anyways, so in conclusion, what we've given you is a quick update on the Universal Library, which is a library with tens of thousands of number systems that you can use to try to tailor the dynamic range of your application with a number system that captures that. It really is being used right now in these two big domains. One is reproducibility in high performance computing and energy efficiency in embedded intelligence. In that latter, we see a need where the CPU and the accelerator need to be collaborative, and the Universal now provides a software development kit in which you can design and optimize these type of mixed precision algorithms. And just to give people, all of this is open source. These are the links that you can use to look at it. One cute example is we have integrated Universal with Jupyter notebooks, so you can try these things in a Jupyter notebook environment and build demonstrations and lectures that way. And that is what I have to contribute for CoNGA this year.
Thank you, Theo. Great. Excellent use of the time. We are taking questions using Pigeonhole. That's www.pigeonhole.at with the passcode SCA22, and the QR code that is being put up on the screen now will allow you to ask questions. While people are getting questions in, I thought of a couple that while you were talking. Here's a really dumb one to start out with. You use the acronym IGA. I don't know that one. What is IGA?
Isogeometric analysis.
Oh, you might want to spell that out next time you make a slice. Don't know that one. Isogeometric analysis. Okay.
Yeah.
Another question I had was, I was surprised you said NVIDIA has a multi-base logarithmic number system now?
Yeah, they patented it. Yeah, Will Dali did. Yeah, I mean, everybody sort of understands that deep learning is a logarithmic number system problem, right?
But is his system similar to that of our program chairman, Vasil Dimitrov?
No, it's slightly different, but Vasil is more skilled in telling the difference. I think the superficial understanding I have of it is that Vasil's multi-dimensional logarithmic number system is truly multiple bases, but in NVIDIA's case, they haven't really gotten to multiple bases and optimizing that second base or third base or fourth base, right? So they're basically two exponents that they use, whereas Vasil is an arbitrary specification of bases.
So they patented their logarithmic number system. They're going to license it and charge for people who use it then?
That I don't know. All I know is that Will Dali filed a patent on multi-base. Yeah.
Okay. We have a question from Santosh. In the context of debugging, Universal is a good experimentation framework for new algorithms. How easy is it to port existing frameworks and solvers?
Really good question. So Gizmo, who was using the linear algebra libraries Eigen and MTL, they had one library that gave some grief, and that was an expression toolkit, and that required some software engineering to figure out. But once that was figured out, and it was probably a 2-week problem, we basically moved 300,000 lines of code to be enabled. So Gizmo can do universal fixed points, posits, C-floats. They have it all. So in general, what we've noticed is when people are not writing their own functions as parameterized functions, right? So when they themselves are not planning for changing doubles to floats or halves, then there is software engineering involved to change their programs to do that. But since linear algebra libraries tend to have had this desire from the get-go, right? Almost all linear algebra libraries have parameterization in their arithmetic types. So linear algebra has been very easy. That autodiff that you saw on the list, that is a modern piece of code that came from CERN. It literally took 5 minutes to enable that with all of the number systems in Universal. But that was because the guys that wrote autodiff, used the modern C++ framework to build their software, and we're ready to receive these different number systems. But in general, we're seeing that on the moment the developers are not planning to even replace their own doubles and floats, then there is a design change necessary to really take advantage of different arithmetic types.
Santosh has a question about the series solver ported to Universal, but we are out of time. It is now officially time for lunch in Singapore. Why don't you take it up with Santosh directly?
Yes, definitely will.
We will reconvene in an hour. Thank you very much.
All right, guys. Take care.